today, for this tech talk, we are going to open the cover on embeddings, specifically embeddings in RAG. So on a typical lag pipeline, what we have is we start with document splitting. Then after splitting the documents, you embed them. Then you put them in a vector database or any other database that you're using. So I'm looking at this part of the embedding. What is embedding? How is embedding done? After that, I'm going to also touch on when a user asks a question, embedding is done, and then you do a similarity search. So we are going to see how all of this is played into the RAG. We are going to open the cover and look deep inside into how basically the embedding is treated. I'm excited to look into this, so let's jump in. So as I mentioned, you can see that typically when we start at when we are doing RAG, we start with the knowledge base, basically all the PDF documents, the docs, the messages, all the documents that you want to comprise the vector database. Then we create chunks, we split them into chunks. Oh, this can also include articles, web articles and all. So then we make chunks. After we make chunks, we split them into different chunks. Then we apply the embedding. Basically on each chunk we add the embeddings, which will give us this vector data, which will give us vector embeddings, these vectors, and then the vectors are added in the vector database. Now let's talk about how in embedding you can use a sentence like this. For example, you have, on Friday I ate an apple while wearing an Apple Watch. And when you're going to embed it, typically an embedding model has a large vocab size, and then it's going to embed it to a vector like this. So this vector is respective to the dimension that the embedding model supports, but it can reach, for the simplicity, we are going to use a 3 by 3 dimension. We are going to use a 3 dimension, but just know an embedding model, a typical embedding model, has something around 730 plus to 1300 dimensions. So this is just for demo purposes to show you how it works, but if you use something like Orama embedding and all of that, it's going to be way longer than this. So this is where we come. Now from our sentence, let's suppose we have our embedding model has this vocab size. So the vocab size is the number of vocabularies it was trained when during the training, the number of vocabularies it picked, and also with respective to their context. You will see why the context is necessary. So we say, for example, it has Friday, it has 8, it has Apple, wearing, and a watch. Now remember that we are saying this is our dimension is going to be this, but now let's see how does it relate now in terms of the dimension. How does it relate to, how do we alive to this vector? What we do is that we are going to now make the dimensions for each, basically the 3 dimensions that we will consider. Let's suppose we consider time, food, and technology. And now for a typical embedding model, it aligns to these dimensions because as it was trained on. So for example, for it could be trained on Friday is the 5th day of the week, containing like all of those training phrases that it has. Then it would understand that Friday, as it pertains to time, in terms of time, it's with close. So we are scoring it 1 as the maximum, the highest maximum, and 0 as the lowest maximum, 0.0 as the lowest, as the minimum. So Friday in close to time is 0.9. Very Friday in relation to food. I guess you can say we ate some food on Monday or on Friday, but this is basically like zero in this dimension. Friday is like 0.1 because it can be used for something but nothing much. Then in terms of technology, the square is 0. 8, same case in terms of time, but 8 and food there is a strong relationship, so we give it a score of 0.8, and 8 with technology really there is no relationship. And for all of the other parts, if you see all the other, and here we are considering the like the words in our in our sentence, ignoring these top words like on, I, an, while, and something like this. So we are ignoring these parts now. Here, and remember we have two Apple words. So we have Apple the flute and Apple the company. Now what's going to happen is that each if you check for Apple the flute, we have a zero point 0.7 because it can either be used as a technology or as a food, and in terms of technology it's 0 0.7. And also wearing, the verb wearing is, we give it the same score, and then also the watch, we give it the same score. Now here we are going to create the average, and when creating the average we consider all the words that we have. So Friday we add, it, we add apple, we add another apple because we have two because we have two apple words, apple the watch, no, the company, and apple the flute. Then we look at wearing, and then we look at the watch too. So we add all of this and then divide by 6, we get this. Same case here, same case here. This is how we get now to our vector that the embedding model is going to add. Now take, this is on a minute detail, but now remember that during RAG, what we are doing, we take this big chunk of a document, and then we split it into multiple documents. Now this is what's happening. So the moment this document comes in, this particular document comes in, this is what's going to happen, and then a resulting part of the a resulting vector is going to be there, same for each other documents. Now we are going to see how this is saved inside the vector space. In our vector space, yes, in our vector space, let me clean all of it. Okay, let me clean the entire thing. So in a vector space, you remember we're using 3 dimensions, so we can just make a 3-dimensional vector space, something like this. So no, it always looks up. Yes, and then we make the last one, which will be a brick. Yes, and let's suppose this is time. You remember we have 3 dimensions. We have time, food, and technology, and then this is food, and then this is technology. So since you have these three, now how will this be? How does the vector space work now? What the vector space does is like we are going to plot this matrix, no, this vector, sorry. So like from like O level mathematics, or really some mathematics from graph mathematics, I would say, or linear algebra mathematics. We plot a point like this. So on the full scale, on the full dimension, we have 0.33. Let's say 0.33 is this place. So we do something like this. and then it goes to 0.44 on technology. 0.44, let's say 0.44 is here, so this is 0.33, and then on yes, this is the 0.33, and then on our time it's going to be time is 0.22. Let's say 0.22 is here. So now you see they meet. This is the resulting this is the resulting vector, and then from the origin it comes like this. Now this is how our vector space is going to this is how our vector this is how our vector space is going to be stored. But what's going to happen now is that so for other documents it will be the same thing. Other documents, maybe depending on their part, like it's going to be like this. Now when you ask a question to our model, to our vector lag, to our, when you embed a question, it's going to pass through the same process. Now the question will come with an array. It will come like with an embedding like this. It will be also a vector. Now the yes, the vector comes like let's look at this. So for example, the vector is why is it now bending? Why would you bend? So we sorry, I've chosen the wrong one. We have a vector like this. Now what's going to happen is, like, let's say you have asked what did the user eat on Friday or something like that, and then it comes, it's going to plot it on the vector inside the vector space, and then it's going to calculate. We have two parts, so two similarity search styles. So we have the cosine search, which is basically measuring the angle between the vector spaces. So between this one and this one, between this one and this one, between this one and this one, and this one and this one, to estimate the similarity. So for example, this one, if it's like 15, then the similarity is you can say that one is very similar. It's nearly similar. If it, so you can see like these two are very similar. But if it's like 180, maybe it's some vector which is like here, then that's an opposite, and then it's and depending on the threshold that you provided, then it will give you based on the one with the near. So we'll look all of this inside the when we are looking at the implementation of similarity search. So similarity search is, now we have another one called Euclidean. Hope I didn't spell that wrong. Euclidean similarity search. Similarity search. Similarity search. What this one is basically doing, the Euclidean part, is now calculating the distance between these two vectors. And how do we calculate the distance? It's just to get this part, so this vector minus this one, changing like the dimensions, then we see what has the greatest distance. So this one and this one, all it will calculate. Let me use a different color to separate this. Yeah, purple, we haven't used purple. So this is the first one, and then we check something like this one too. So this one, you see, it's looking at like the distance between the two, and now from the distance it will return the vectors, or the embeddings, the vector embeddings that have the distance, that the shortest distance. So